Now in example 7, we have f of x equal to 5x over absolute value of 3x minus 4, and g of x equal to absolute value of 2x minus 5. And with the work I did beforehand, we can see that the domain of the function g is all real numbers, but the domain of function f is going to be a little different. Although it's a rational function, we got to take out the denominator and set it not equal to 0, because that's how we start finding the domain of any rational function. But because the denominator is an absolute value expression, we want to recall the definition of absolute value function. We'll recall that if we have the function absolute value of x, it can be written as a piecewise function where it is going to be equal to positive x if x is greater than 0. It is going to be equal to 0 if x is 0, and this function equal to negative x if x is less than 0. Well, the same thing can be said for here. If we have absolute value of 3x minus 4, then its piecewise form, actually I'm going to write it down here for more room, easier to see. Absolute value of 3x minus 4 is going to be equal to the piecewise function of positive 3x minus 4 if 3x minus 4 is greater than 0. It's going to become 0 if 3x minus 4 is equal to 0, and it's going to be negative 3x minus 4 if 3x minus 4 is less than 0. And of course, mentally solving for x, I can tell that this basically indicate has to be greater than 4 over 3 if I solve for x, of course. This right here would indicate x equal to 4/3, and this would indicate x less than 4/3. So absolute value of 3x minus 4 is going to become 0 if x equal to 4/3. So we can tell right away that the domain of this function f is going to be all real numbers except x cannot be equal to 4/3. And the interval notation is negative infinity all the way to 4/3, but not including it, union 4/3 all the way to positive infinity, like that. Now let's find the quotient f over g. So f of x over g of x equal, well, f of x is 5x over absolute value of 3x minus 4 all over absolute value of 2x minus 5. And of course, this is a rational function, so I want to be careful. Looking at this denominator, just like up here, I know that x cannot be equal to 4/3. So that's one restriction for this steps. But there's another restriction. I have this denominator absolute value of 2x minus 5. So what I'm going to do is that I got to recall the same piecewise manner. I mean piecewise function, but for this absolute value function. So absolute value of 2x minus 5 is equals to positive 2x minus 5 if 2x minus 5 is greater than 0, 0 if 2x minus 5 is equal to 0, and negative 2x minus 5 if 2x minus 5 is less than 0. Of course, solving for x, you can tell right away that this is the same as saying x greater than 5/2, x equal to 5/2, and x less than 5/2. Hopefully you can see it there. So yeah, this is a piecewise function of absolute value of 2x minus 5, which is the denominator here. And looking at this piecewise function, we know that the denominator absolute value of 2x minus 5 is going to become 0 if x is 5/2. So really another restriction is x cannot be equal to 5/2. Anything by itself is the same as itself divided by the invisible positive 1 denominator. So change this division into multiplication by keeping the numerator the same. And multiply by the reciprocal of the denominator, which is just 1 over 2x minus 5. And of course, at this steps, same thing. X cannot be equal to 4 over 3 and 5/2 if we observe these two denominators. Now, how do we simplify it even further? I mean, how do we multiply it out? Well, for the numerator, it's easy. 5x times 1 is just 5x. For the denominator, since absolute value is distance, and distance is always positive, it is okay to write absolute value of 3x minus 4 as parentheses 3x minus 4. And same thing for this absolute value, so 2x minus 5. And of course, put it inside one common absolute value. Okay, and of course, the restrictions are still going to be the same. Because if I take any one of these x value and plug it into its respective place, one of these two binomials is going to be 0. 0 multiplied anything is 0, and this whole denominator will be 0, which would make this steps undefined, and then everything else will be undefined. We don't want that, so that's why the restriction is still the same. And foiling it out, I'm going to have, let's see, it's 3x, absolute value of 3x times 2x is going to be 6x squared. 3x times negative 5 is negative 15x. Negative 4 times 8x is going to be minus 8x. Negative 15x minus 8x is going to be negative 23x. And then plus 20. And of course, restrictions are still the same. Because here, from here to here, it's just foiling it out while keeping the numerator the same. So that's f over g of x. Now what about g over f of x? Well, let's see. G of x over f of x. What g of x is absolute value of 2x minus 5. And f of x is 5x over absolute value of 3x minus 4. Now we got to be careful with these steps. Looking at this little denominator, we can tell that x cannot be equal to 4 over 3 as usual. But at the same time, we have to consider the entire denominator as well. So we have to take this whole denominator, 5x over absolute value of 3x minus 4. And we set it not equal to 0 because, you know, it's a rational equation. Multiply both sides by absolute value of 3x minus 4. So I'm trying to squeeze it in right here. In order to get closer to x, you know, this would cancel out. So left hand side we're left with just 5x. Cannot be equal to 0 multiply anything is 0. So x cannot be equal to 0 as well. So you see, that's why whenever we deal with rational function, we want to make sure that we take a look at all the denominators. All the denominators on the outside and all of the ones inside as well. Or the smaller one, I should say. So this step has a restriction of x cannot be equal to 0 and 4/3. Well, let's simplify even further by change this division into multiplication by keeping the numerator the same, which is absolute value of 2x minus 5 divided by the invisible positive 1 denominator, and multiply by the reciprocal of this denominator fraction, which is absolute value of 3x minus 4 all over 5x. But we can tell at these steps that x cannot be equal to 0 because of the denominator 5x here, and we know that it's up here. And then multiply everything together by recognizing the fact that the denominator is the same, which is 5x. But the numerator is going to be the same as what we did earlier, which is just absolute value of 6x squared minus 23x plus 20. I'm not going to write out a work because you guys know how to do it. And of course, x cannot be equal to 0 at this steps. So let's sketch the domain. So this is a number line. And for f over g, let's see. I got x cannot be equal to 4/3. Well, I mean, up here, actually, I got x cannot be equals to... yeah, x cannot be equal to 4/3. X cannot be equal to 4/3, and x cannot be equal to 5/2. So I'm going to put, what let's see, maybe zeros right here. 4/3 is like 1 something. So maybe 4/3 right here. And maybe 5/2 is here. Yeah, because 4/3 is same as 1 followed by 1/3, and 5/2 is 2.5. Now, domain of the function f is, as you see here, all real numbers except for x cannot be equal to 4/3. So put the open circle here and sketch the domain of, oops, that's a bad one, of the domain of function f. Now, domain of function g is, as you see, all real numbers. So it's just that. But the restrictions of the simplification, the restrictions from domain of function f, domain of function g, and every step of the simplification process of the quotient f over g are just 4/3 and 5/2. So put the open circle here and put the open circle here. And collecting everything, collect all of the x values in common and collect all of the restrictions, we can tell that the domain of f over g are all real numbers except x cannot be equal to 4/3 and x cannot be equal to 5/2. And the interval notation is from -infinity all the way up to 4/3, but not including 4/3, which is just this part. Union, to jump to the next part, we go from 4/3, not including 4/3, all the way up to 5/2, but not including 5/2. So 4/3, comma, 5/2. And then union to go to this part, from 5/2 all the way to positive infinity, but not including 5/2. And that's the interval notation for the domain of f over g. Now, what about g over f? Let's see. Domain of f, x cannot be equal to 4/3, no restriction from the domain of g, and in the quotient g over f, x cannot be equal to 4/3 and 0. So I'm going to put 0 here and 4/3 over here. And of course, sketch the domain of the function f and g, which are the same. And since x cannot be equal to 0 and x cannot be equal to 4/3, all of the restrictions, the domain of f, domain of g, and every step of the simplification process of the quotient g over f, the domain of g over f are all real numbers except x cannot be equal to 0 and 4/3. And the interval notation is from -infinity all the way up to 0, but not including 0. Union from 0, but not including 0, all the way up to 4/3, but not including 4/3. So 0, 4/3. And then union from excluding 4/3 all the way to positive infinity.